Number 35. If 1.000 grams of 26 radium produces 0.0001 mils of the gas 222, so 222 radon, at STP, which is standard temperature and pressure, in 24 hours, what is the half-life of radium-226 in years? Okay, a lot of stuff to unpack here, so let's get down to it. Now, the first thing that I notice is that we are going from one isotope, so we're going from radium to radon. So we're going from Ra to Rn. Now, anytime that they're giving you, values and talking about half-lives, especially if they're giving you single atom isotopes, I don't care whether this is carbon or uranium or, barium or whatever, this is all under the scheme of radioactive decay. And the good thing about radioactive decay. Now, the good thing about radioactive decay is that this all abides by first order kinetics. And it goes by for all isotopes. So I don't care, radium, radon, uranium, palladium, like plutonium, bismuth, right? Lead, I don't care. They're all going to have the same formulas. And it's those formulas that you learned when you did your kinetics chapter, which are these two formulas down here. Now, a lot of times, because this is a nuclear chemistry chapter, they're going to want to make you memorize new formulas. But I say, why? Right? If you already learned the formulas here and they're the same exact ones, just use these. So that's what we're going to do here. So as far as formula-wise, if you guys did your kinetic formula, did your kinetic chapter, you already know how to use those formulas. So now we just got to dig in and answer the problem. Now, we are, at the end of the day, right, we want to find out what that half-life is. And according to our two formulas from first-order kinetics, a half-life is a T-half. So that's the issue here. We're trying to find out a T-half. And between these first-order kinetic equations, there's only one of them that has the half-life. So we know at the end of the day, we have to be using this formula. This has to be our X value. Now, the 0.693 is a given value. That's the ln of 2. But in order to use this formula, we need a K value, and the K value is the rate constant. So now, let's see. Did they make it easy for us? You probably already know the answer. But did they give us a rate constant here? I don't see it. They gave me an amount of the radium. It produces an amount of mils of gas. I don't see any rate constant. So now, that's the next thing. In order to find out that half-life, which is the question, we first have to find out the rate constant. So that's where we hold off for this for a little bit. We got to work separately because now we're going to bring in this formula. This is your other first-order kinetic equation that deals with decaying amounts. And here is the K value. So now we know that this is what we're solving for, which means that we should be able to have all the other three variables. Now let's see here. Let's start off with, these brackets with the A's and the A notch. These are your amounts. And from what is decaying, right, there's always an initial amount and a final amount. Now specifically, if we're looking for the half-life of radium-226, these have to be only for 226 radium. 222. No, Christina. So we need to find out the initial amount. That's this notch here. 0 means that 0 time has gone by. So this is your initial amount. And this would be the final amount of your radium remaining. Okay, so let's see. Did they tell us any of this? Well, they definitely told us that we had 1.000 grams of the radium. And then over time, that's going to produce this amount. So, from the context, this has to be the starting amount. So this is definitely the initial. So at least we have that, right? The initial amount, they told us that we're starting off with 1.000 grams of the 226 radium. Okay. Now let's try to find that final amount. Now it says that it's going to produce this amount, but that's in radon, not radium. Are we sick and tired of the RA words? Right? Radon, radium. But bear with me, guys. We're getting it done. So, did they tell us the final amount of the radium? No, but they did tell us that it produced this amount of the radon. And they're giving us context of STP. Now, STP has some information in there, right? STP is always standard temperature and pressure. So for the temperature, the temp is always going to be, for standard temperature and pressure, the temperature is always going to be 273 Kelvin. And the pressure is always going to be 1 atm. So just knowing this will help us out. Now, with that STP, they also told us that we produced a volume. So I know that now we have a volume, 0.0001 mils, and that's of the Rn, right, the radon. But we're starting to pull together some variables. Maybe we could use another formula, PV and a T. Any formulas that are coming out of the woodwork? Did you say PV equals nRT? If you did, you were absolutely correct. So now we got to go even farther back. I love this question. But we have to do this because we still haven't had a final amount. So let's see. Now, if we're using this formula, right, the pressure has to be an atm, and thank you very much, we have 1 atm. So we're good with that. The volume has to be in liters. But they gave us a mils, but that's okay. We can go from mils to liters, right, of the 222 radon. Mils to liters, all we're doing is we're just dividing by 1,000. So I'm going to take my 0.0001 divided by 1,000. And 3 zeros, right? After the decimal, 1, 2, 3, 1, 2, 3. Yep, so 1 times 10 to the negative 7th liters. Okay, so we have that value. 1 times 10 to the negative 7th liters. Now, the N value is the moles that is being produced, which they didn't tell us that. So we're probably going to solve for that, but let's just see. R is the constant number, 0.08206, and the units there are atm times liter divided by mole times Kelvin. That's why all of these formulas have to be super, super, super specific. And the temp is in Kelvin. And we do know that it's 273 Kelvin. So, in this case, we are solving for the moles of the radon. All of this information is for that radon. It is not for the radium. So, we're going to find out the moles of the 222 radon. So, let's find it out. So, we got PV, so 1 times 10 to the negative 7th equals N times 0.08206 times by the temp, which was 273. All right, let's just clean this up a little bit. This would be 1 times 10 to the negative 7th equals 0.08206 times 273. Okay, so we get 22.40, I don't know, 2. And that's times n. Divide by the 22.402 on both sides. So I'm just going to take these two values, this divided by this. It's good not to round until it's your final answer. But now we know that we have 4.46, I don't know, 38 times 10 to the negative 9th, and that's moles of moles of the 222 Rn. Okay. So now, I guess because we're running out of room here, let's pause the video. The only thing that we basically need to know is that we produced this amount. So what I'm going to say here is I'm just going to bring this up. So this 1 times 10 to the negative 7th liters correlates with a 4.4638 times 10 to the negative 9th moles of the 222 Rn. So let's pause the video if we need to, just to write anything down. But all this Pb equals n R3 and R3, Pb equals n RT stuff is going bye-bye. So bye-bye. Okay. So now, the question is, we still need to find that final amount of the 226 radium. But we have the amount of moles that were produced from the radon. So, if we wanted to, we could write a balanced equation going from the radium to the radon, right, in nuclide notation. If we started off with 226 Ra with an atomic number of 88, this will turn into the radon, so 222 Rn-86. And just know that if you wanted to balance it, right, all the top numbers across the board have to equal, and so do the bottom numbers. So I have a atomic mass of 226, but then 222 plus what will get me 226? Yeah, this has to be a 4. And then do the same thing for the bottom. 88 equals 86 plus what? Yeah, this has to be a 2, because 86 plus 2 is 88, and then the same thing for the top. But now who is this particle, right, or this atom? You could always look on the periodic table. This is a 2, and 4 and 2 is always the helium. This is alpha emission. Helium, that's a 4 on the top and a 2 on the bottom, is alpha. But the basis here is that since we were able to write a balanced equation, just see how many of each isotope you need. You only have 1 radium, and the numbers worked out perfectly so that you only needed 1 radon. So, if you had 4.4638 times 10 to the negative 9th moles that were produced here, and it's a 1-to-1 relationship, that means that how much radium did you use? Yeah, if you produce this amount of moles, that means that you used up 4.4638 times 10 to the negative 9th moles. Were used. So we're getting there. We're almost getting there, right? This initial amount was in grams. We're at moles of the radium. So now let's just convert over the 4.4638 times 10 to the negative 9th moles of the radium into the grams to see how much was used. Okay, so we have to use the atomic, well, the mass number here, right? So grams to moles, all we have to do is just times by that atomic mass. So times by 226. You could also do it the dimensional analysis way, but this is like the quicken way. So I'm just going to take this times 226. Okay, and now we have 1.0088 times 10 to the negative 6th. 10 times 10 to the negative 6th grams of the radium. Now keep in mind that this one was used. But when you're using this formula, it's always the final amount that's remaining. So if you used up 1.0088 times 10 to the negative 6 grams from an initial 1 gram sample, how much grams are remaining? Yeah, you would just have to subtract them, right? The 1.000 grams that were initial minus the 1.0088 times 10 to the negative 6 grams that were used is going to give us finally the final amount. So I'm just going to take 1 minus this number. And yeah, I mean, we get 9.99999. So 0.99, we'll pull it out to 1, 2, 3, 4, 5 nines. Okay, and that's the grams that are remaining. So that's now finally the number here. 99999. Okay. Finally, we have a final amount. We had an initial amount. We're now searching for the rate constant because remember, the idea at the end of the day is to plug in that rate constant here. Now, the last thing is, what is the time? Now, we do have, it produces the 0.0001 mils in the 24 hours. So this is going to be 24 hours. Okay. So, pause the video. We're going to get rid of this because we don't need it anymore. And now we're going to finally do this formula. So, bada bing, bada boom. There we go. And let's plug in everything that we have. This question is absolutely nuts. ln equals negative plus the ln. Okay, so we have 0.99999, which I'll use the full number here, equals negative x times the 24 plus the ln of 1. Okay. So, let's go for it. We're going to do this ln value. So, ln of this whole thing is that number, negative 1.0088 times 10 to the negative 6th equals negative, we could do 24 times x, plus the ln of 1 is just 0, so we can get rid of this. And now, all we have to do is just divide by negative 24. But remember, that's not the final answer. That's just the rate constant. So we have x equals, we'll take this value and divide it by the negative 24. Okay, and we have 4.203 times 10 to the negative 8th. And since the time was in hours, this would be in hours to the minus 1. Okay, so this is now your rate constant, which we finally found out here. So this now is going to be 4.203 times 10 to the negative 8th hours to the minus 1. So finally, we can, maybe I do need to pull that up. Finally, we can use this formula. So let's go. So T half equals 0.693 divided by that K value, 4.203 times 10 to the negative 8th, 0.693 divided by this number. Wowsies. So you get a T half of a lot of hours, right? 1.64, I guess we'll say 1.649 times 10 to the 1, 2, 3, 4, 5, 6, 7. And since your first time that you used was in hours, the K value was in hours, this has to be in hours. However, it said that we wanted the half-life in years. It kind of makes sense because the hours are so much. So, how do we go from hours to years? Let's see. Maybe what I'll do is I'll pull this to the side. And we'll pull this. Actually, what we can do... We're making room. We are making room. There we go. So now the last thing is to just convert from hours to, what do we want, years? Okay, well, we can go from hours to days and days to years. So if you can do that dimensional analysis if you want to, I guess we can because we have a little bit of room. So 1.649 times 10 to the 7th hours times by a ratio. Let's go to days first. So hours on the bottom, days up on top. There are 24 hours in one day. So that gets rid of the hours. And then, on an average, days on the bottom, years up on top. There is generally, in 1 year, there's 365 days. And now, we have the unit of years. So all we have to do is take this value, divide it by 24, and then divide it again by 365. Wow. So this is 1,882 years is a half-life, which means that it's going to take 1,882 years for that radon to decompose to half its size, which is absolutely incredible. Such a long amount of time. But it makes sense because usually with those big elements, it will take a really long time to decompose. So yes, thank you so much for viewing the video. This has been a journey. If you guys are still with me, thank you so much. I really hope this helped. If you know how to do this one, I think you're really good at chemistry. So you should be proud of yourself and give yourself a pat on the back. I'm going to give myself a pat on the back. Woo-hoo. Some of these problems I'm like, wow, okay. I can't believe they're, some of these problems, but we made it through. I hope you're having a great day out there. And hopefully it's a little bit better after this grueling question. But anyway, if you want to, you can press the subscribe button if you haven't already. Thank you so much. If you want to be a member to the channel, you can be a member. Not obligated though, obviously, but anything, any little bit helps. Thank you so much. And I'll talk to you in later lessons. Okay. All right. Bye-bye.